Right now, the starting salary for electrical engineers is above $50,000 a year. It's running about $60,000 a year. But let's say you start off with 50K, and you're going to save 15% of that. A lot of money managers said this is the key to wealth. When you first get out of college, you're used to living on nothing, especially for electrical engineers. You guys are going to be making substantially more than many of your classmates, substantially more, way more than 15% more. If you take a look at the average difference in salary between electrical engineering and, say, a philosophy major graduate, you guys are going to be making not quite twice as much, but right now the statistics say about 80% more. You can save 15% of that without thinking twice about it. It will not make a substantial difference in your living. And let's say that every year you get a 2.5% raise. And on average, your investments, that the 15% that you invest, earn 7.5% in interest. And the question is, how long will it be to be a millionaire? Your friends who are in economics and business have a book of formulas. And if the formula to solve this problem is in it, they can plug it in and they can get a response. If it's not in it, they don't know what to do. They'd have to put it into an Excel sheet and program it through. I'm going to show you how to use Z-transforms to analytically derive it. I'm going to call this rate 1, and I'm going to call this rate 2. So let's model what's going on. It turns out that this saving money is tricky to model. So I'm going to recast that as saying, what is 15% of 50K? That's hard. If it was 100K, 15% would be...
It's 7.5.
It's 7.5. And the way that I would think about it is that if it was 100,000, it's 15%. So half of that would be half of 15. So it's 7.5K. So the way to model all this is you've got a 7.5K impulse. So here's the sequence: 7.5K at n equals 0, your first year, at the beginning of your first year, and after that it's 0. And by the way, I'm going to give you an example of this as a block diagram, which is also going to be really useful to you on your tests. Whenever you have something that starts off at some value and it increases at a particular rate, that looks like this. That looks like this. At n equals 0, you have 7.5. At n equals 1, nothing comes into the left, but now you've got your 7.5 over here multiplied by 1 if our R was 0, and we'd have 7.5K again, and then that would be delayed, multiplied by 1, 7.5K. So now you're getting if R is 0, now you get a constant 7.5K every year. But if we multiply it by R1, now it's going to be increased by R1% every year. So this represents how much saved at year N. And then you can kind of see it's the same exact process for earning your interest. This will be 1 plus R2. So this is how much saved. And let's just see intuitively what's going on. Let's say it's a different problem and we just put in $1 at the very beginning and you never put in another $1 and you're not earning any interest. R2 is 0. You put in $1, And then the next year, nothing comes in here because this was an impulse. You just put in $1 into your savings in year 1 and at year 0, and you never added anything more. But that dollar that you had at year 0 gets delayed. So now it's year 1, we're analyzing it, multiplied by 1, and you still have that dollar. And at year 2, delayed, times 1, you still have that dollar. And now if R2 is not 0, now that dollar is growing in value every year. And now the whole thing is that it's going to be compounding whatever you're adding into it every year and compounding it with interest. So this is how much you've saved, and let's call this Y of N. All right, now the rules for finding out how to, the rules that let you transform a block diagram into a Z transform is this. Number 1, you're going to write a new variable at the output of every summer, if there's not already a variable defined. And then you're going to write an equation around each summer. So let's do that quickly. A new variable at the output of every summer. So this is an output. We don't have a variable. So I'll call that S of N for how much you're saving in that particular year, not how much you have saved total, but the amount of savings that go into it. And let's see, and this already has a variable, it's Y of N. So we're done that. Now we're going to write the equation around every summer. I'm going to transform it into the frequency domain. So this, in general, is my input, right? So in general, this will be my X of Z. And that means that this will be my S of Z. Delay it by 1 and multiply it by 1 plus R. That means it'll be 1 plus R1 times Z to the negative 1 times S of Z. And let's see, this is S of Z, we said. This is Y of Z. So this would be Z to the negative 1, 1 plus R2, Y of Z. Now we've done step 1. And now let's do step 2. Writing the equation around every summer. We'll do it around the first one. This looks almost like doing KCL, doesn't it? The output is S of Z. And that equals this, X of Z, plus 1 plus R1 times Z to the negative 1, S of Z. And we could pull our S's on one side and our X's on the other. If we move our S's to this side, we'll have 1 minus 1 plus R1 Z to the negative 1. So this is all of our S's on the left, and then our X's on the right. And now let's do it at the right sum. Doing it on the right side, around this side, we have our output, which is Y of Z. And that equals our input, S of Z, plus this guy. So that's Z to the negative 1, 1 plus R2, Y of Z. Let's do the same trick. We'll put our variables on each side. So our Y of Z is on the left. That gives us 1 minus Z to the negative 1, 1 plus R2 on the left, and on our right is S of Z. All right, so now we've got our two equations. And we want to find our output as a function of our input. We want to get rid of our S's. Well, it looks like we've kind of already done that over here, right? So every time I see an S in the top, I'll just plug in this. So our single equation now is going to be our S, which is this. And then I plug in the rest of my equation up here. And now I can divide through to find my system transfer function. H of z is just defined to be my output over my input. So that would be, from this thing, 1 over 1 minus z to the negative 1, 1 plus r2, times, I'm going to make these brackets a little different to make it clearer what bracket is what, times 1 minus z to the negative 1, 1 plus r1. And that's pretty cool. We've now got our transfer function. Now we can find what our output is. Our y of z is our transfer function times our particular input. So our particular input is just the transform of this. So that's going to be 7.5 K. That's its transform. And then we're going to multiply it by h of s, which is 1 minus z to the negative 1. And we said, let's see, what do we say R2 was? We said R2 was R2 was 7.5, so it'd be minus 1.075 z to the negative 1 times 1 minus 1.025 z to the negative 1. And now, you know that's equal to, here's our partial fraction decomposition. Where you find this guy by covering up the corresponding z to the negative 1. And you can see z to the negative 1 is going to be 1 over this. So it's going to be, the numbers get a little bit nasty. 1 minus, this is going to be 1.025 times 1 over 1.075. And this whole thing, it turns out to be 161.25, and this turns out to be minus 153.75. These are both K's. That sounds pretty horrendous. That means our y of n is going to be equal to, I'm just going to call this whole thing, to make it easy, I'm going to call this K sub 2, and I'm going to call this whole thing K sub 1. And the formula of our output is going to look like K1 times R sub 1 to the n plus K2 R sub 2 to the n. I mean, it's exactly going to be minus 153.75 thousand. Whoops, that should be this, I'm sorry. Times 1.025 to the n plus 161.25 thousand, 1.075 to the n. And all of that times our u of n. And when you plug in y of 29, it's equal to 1.031 thousand. So after 29 years, if you are good about putting away 15% of whatever your take-home income is, you'll reach a savings of $1 million. And because it's exponential, you know, it might have taken you 29 years to reach that point. But after another 10 years, you're up at about $2.5 million. And if you decide, and you know, at that point, at 39 years old, after working for 40 years, you can retire on a $2.5 million nest egg, on top of your company's retirement pension, on top of Social Security, which probably won't exist for you, but you won't need it because you'll have your company's pension and you'll have a $2.5 million nest egg. Any questions about all that? The numbers, I'm sorry, they get nasty when you do the real world problems, but I think it's useful to see how powerful this is in different fields of study.